Okay, in this video I want to explain in a bit more detail why our electrical mains systems are set up in the way they are, and why earthing is done in the way it is. Because if you've learnt a little bit about earth wires, live wires, neutral wires and earth wires at GCSE, you might have a few questions about why the system is set up like this. It sounds quite complicated. Why do we need these three wires? What are they all about? I'm going to try and explain it from the point of view of me being a physics teacher and having some knowledge of physics. I'm not an electrician, and I don't actually run national power grids. So if you do become an electrician, or you do want to start a national power grid, don't do it based on what I've told you in this video. Definitely get some more training before you do that. So in the real world, things are always more complicated than the simplified pictures we paint as teachers, but hopefully this series of simplified pictures will help you understand a little bit more what's going on. So I'm going to take you through a few different models, a few different ways that power distribution systems could work, and how they do work in some places and not in others. So they're all going to relate to a power station which is far, far away, which is producing AC, and then if you know about the power grid in the UK, you know that AC is stepped up through the pylons and then stepped down before it's supplied to houses and stuff, and it's stepped down using a transformer at a substation. So here's the transformer. It's got two wires on the left which go off back to the power station. Then it's got two connections on the right. This is where we're going to get our mains electricity, 230 volts AC coming out of that. Now, method one of power distribution would be to make what's called an isolated electrical supply, which has some benefits to it and some drawbacks. So what we have is a wire coming from one terminal here and a wire coming from the other terminal there. These are insulated wires, and nothing in this system here is connected to the ground, to the earth itself. So the transformer is like our power supply in this circuit, and then we've got two wires coming from the power supply with an AC voltage of 230 volts between them. Okay, so if you plug something in between these two wires, if you connected a mains bulb between these two wires, it would light up. It forms a complete circuit from the power supply, which is the transformer here. Ultimately it's the power station, but we'll just consider the transformer. This forms a complete circuit going through the insides of the transformer, and the bulb will light. Excellent. Now, let's just get rid of those dotted lines. And the bulb, in fact, what properties does this system have? No, let's leave the bulb in, why not? It's not doing any harm. Well, this has some interesting properties. Property number one: if you touch both the wires at the same time, okay, so if this is a person and they touch the top wire and the bottom wire at the same time, they form a complete circuit with the substation. Therefore current will flow through them and they'll experience a bad electric shock because it's 230 volts. So this is not to be advised in an isolated system to touch the live and the neutral. Excuse me, not the live and the neutral. They are not live and neutral yet because we haven't made one live and one neutral, so disregard that. To touch both the wires in an isolated system simultaneously is a bad idea. You're going to get an electric shock. But the interesting thing about this is that nothing is connected to the earth. So if you touch one wire and you are also connected to the earth because you're standing on it, that's totally fine in this isolated system. Because the substation transformer is not connected in any way to the ground, because all the wires are insulated, current can't flow through the ground back to the substation and form a complete circuit. So you can touch this bottom wire here alone and you'll be totally fine. You can touch this top wire here alone and you'll be totally fine. So this system's pretty good. You'd have to touch both of the wires at the same time for there to be a problem. So on the face of it, this seems like a pretty decent system. You'd have to literally touch both the wires to get an electric shock. Otherwise, you're totally fine. Furthermore, what happens if we've got an appliance or something like that with a metal case. If you've got an appliance with a metal case, so let's say we've got a kettle, going to try and draw a kettle somehow here. Okay, here we go, and the kettle's got a heating element inside it here. Okay, one of these wires connects to this part of the heating element, one of them connects to the other. Presumably the kettle also has a switch, and presumably the kettle also has a fuse in the plug. Okay, but we'll just ignore it for now. Now, here's the kettle working, current's flowing through it, it's boiling your water, but let's say there's a problem and one of the wires touches the case, the metal that the outside of the kettle is made from. Does that pose a problem? Well, no, we've just discussed this. You know, if you touch the outside of this, you're just touching effectively one of the wires, but the wires aren't connected to the ground anywhere else, so current can't flow through the ground, so you're totally safe. So this is basically fine. You don't need to even bother connecting anything to a metal case in this system, because nothing's going to happen. If both the wires became disconnected somehow, you know, your kettle's really dodgy, and then both the wires touch the metal case, then you would get a big current flowing through the metal case. The fuse would blow and it would be safe. So it's sounding pretty good so far, this system. Can't see many problems with it. However, oops, sorry about that, just went to the wrong page. However, there is a big problem. Okay, the big problem with this system is that the local substation supplies loads of houses. It supplies loads of houses all branching off this, so you know there will be some wires coming off here to go to one person's house, some wires coming off here to go to somebody else's house. Within your house, these wires branch off in loads of places to all your different plug sockets, and with all of that there's the potential for something to go wrong. What can go wrong anywhere in this system is that the insulation of one of the wires could be damaged for some reason by a mouse or by a spade, someone digging or anything, and one of these wires could inadvertently come into contact with the ground itself, with the earth itself. Either this wire or the other wire, doesn't really matter. Okay, I might make it for the purposes of this one here, we'll make it this wire here gets connected to the earth. I'll draw an upside down earth symbol. So somewhere in someone's house, in someone's garden, where there's a cable running through, somewhere one of these wires is no longer insulated properly and is touching the earth, the ground. Okay, then all of a sudden the properties of this system totally change. Previously, as I've mentioned, if you touched one of the wires you were totally fine. If you touched the other wire you were totally fine. It's only if you touch both the wires at the same time that you have a problem. But now, somewhere, one of the wires has become connected to the ground itself because the insulation has been damaged. Now this system will continue to work completely normally in that situation. Okay, completely fine. No one's going to notice that this has happened, except if your kettle has this fault here, okay, where one of the wires is touching the metal case. Now, one day you go to touch your kettle, and now current can flow through the ground to this wire here. So current can flow through this wire here, through the metal case, through you, then back to the other wire, through the ground itself, which you were in contact with, to this fault here in the other wire. So all of a sudden, because of something that's happened in someone else's garden, because of something that's happened in someone else's house, suddenly your system, which was safe if one wire was touching the kettle, is now not safe. Furthermore, if you're an electrician and you work with this sort of system, one day you're working on the system and it's totally fine to accidentally come into contact with one of the wires. It's fine if you just brush up against one of the other wires, that's not a big problem for you. Okay, but as soon as this fault occurs somewhere in someone's garden, in someone's house, then one day you touch one of the wires and it's totally fine, you touch the other wire and you get a really bad electric shock. So this system basically is unpredictable. If nothing goes wrong anywhere in the system, it's actually really safe, because you'd have to touch both the wires to get a shock. But as soon as something goes wrong somewhere, you know, one or other of the wires suddenly becomes really dangerous to touch. So this system isn't used for like widespread mains distribution to houses and stuff like that. It is used for very small scale applications, just with perhaps literally only one appliance attached to it. So in bathrooms, you get isolating transformers like this, which literally supply one socket for a shaver or something like that, or for an electric toothbrush or something. So there's not this big distributed system where something could go wrong. It's literally just one appliance. So isolated electrical supplies are used, but they're not used for big supplies to homes, because if one thing goes wrong in one place, suddenly the system becomes dangerous. So what could we do then to get rid of this unpredictability and this uncertainty from day to day about wires being dangerous or not dangerous? Well, we could move to a live and neutral supply, where we've still got two wires coming out of the substation, but one of them we deliberately connect to the ground. So at the substation we put a massive stick of metal into the ground and connect one of the wires to it. Okay, and we call this wire the neutral wire and the other wire the live wire. What properties does this system have? Well, if you touch both the wires at the same time, you get a really bad electric shock because you form a complete circuit with the substation. If you touch the neutral wire, that's okay. It's not going to form a complete circuit between you and the live wire and therefore the substation, because the live wire is not connected to the ground. Okay. However, if you touch the live wire alone and you're also in contact with the ground itself, then current can flow through you, through the ground itself, back to the local substation, bypassing the neutral wire entirely, and you'll get an electric shock. But this situation is predictable. We know what's going to happen. Whoops, sorry about that. My board's not very well calibrated. I keep hitting the wrong button. So this situation is now different from the isolated situation. Now one of the wires is always dangerous to touch. The live wire, the one that's not connected to the earth at the substation, this is always dangerous to touch. This one is theoretically safe to touch, but I wouldn't touch it anyway because there are some faults that could occur to make it no longer safe. Okay, so this is neutral with respect to the ground, and if there are no faults it would be theoretically okay to touch it, but this one's always dangerous to touch. So this just removes the uncertainty that there was in the isolated situation. Now we know what's what. Okay, now if some of the insulation of the neutral wire gets damaged and it gets connected to the ground over here, it's no big issue. Okay, you know, it was connected to the ground somewhere else anyway. If some of the insulation of the live wire gets damaged so that it comes into contact with the earth, now a big current is going to flow. Well, it depends on how the resistance of the path through the earth, but certainly a current is going to flow straight away through the ground, which can hopefully be detected by a circuit breaker tripping or something like that. So in this situation, wires coming into contact with the earth will either hopefully trip a circuit breaker or not be an issue. Now, what happens if the live wire touches the metal case of an appliance? Well, let's get our appliance again, which is now just going to be a box for ease of drawing. This is an appliance with a metal case. Inside it, usually, the wire is just connected to some sort of heating element or something like that with a switch and a fuse in the plug, and everything's working fine, but somehow a bit of live wire manages to touch the metal case. Now you know the situation here. The situation here is if you touch the metal case when the live wire is in contact with it, current can flow through you, through the ground, back to the power supply, which is in this case is the substation, and you get an electric shock, which is bad. So you might think, okay, well what we could do is just connect the neutral wire. Let's branch off here with the neutral wire and also connect the neutral wire to the case, to the metal case. That seems like a good idea, because watch what happens. What happens if a bit of live wire somehow becomes detached and touches the metal case? Well, a big current flows. A big current flows through the metal case, back through the neutral wire, and the fuse blows. So the fuse inside the plug for this appliance blows. So we're safe. Okay, if the live wire touches the case, big current flows, fuse blows, we're safe. Woohoo! Okay, so this seems like pretty good basically. We don't need an earth wire. What was the earth wire for? Why have we got an earth wire when we could just connect the neutral up to the case? Well, there is one big drawback to this. Okay, one huge drawback to connecting the neutral up in this way to the case, and that is again if a problem happens somewhere in the circuit, and namely that problem is one of the wires getting cut and not the other. So remember, this is a big distributed system. We've got live wires branching off here to go to people's houses, neutral wires going off here, a live wire going off here to someone's house, and all these are going underneath roads, or they're going overhead cables or something like that. Now it's possible, although very unlikely, it's possible that somewhere the neutral wire gets cut but not the live wire. Now this can happen, but it's not massively likely. Okay, now if this was our setup where we had the neutral wire giving us our protection against the live wire touching the metal case, now we've got a massive problem. Okay, previously when this was connected, it was totally safe to touch the metal case. By touching the metal case, you're effectively touching the neutral wire, but the neutral wire, clues in the name, is neutral because it's shoved into the ground somewhere, so it's at the same potential as the ground. But if the neutral wire gets cut, now there's a massive problem. What happens if you touch the metal case of this appliance now? Watch very carefully. Current can flow through the heating element of the kettle or whatever, through the neutral wire that's connected to the metal case, through the metal case, through you, through the ground which you're standing on, back to the local substation, and you can get an electric shock, a bad one. So we could just have two wires, a live wire and a neutral wire, and we could connect the neutral wire to the metal case of appliances to give some protection in case the live wire comes into contact with the case, because it will blow the fuse. But it does run the risk of somewhere in your house or somewhere down the street the neutral wire getting cut and the live wire not getting cut. All of a sudden, all of your electrical appliances with metal cases that were switched on at that point would become instantly live, and if you touch them and you touch the ground at the same time, you'd get an electric shock. So it's not favoured, this system, for that reason. So just having a live and a neutral wire isn't widely used, and with the neutral wire providing this protection, because if the neutral wire gets damaged or disconnected somewhere, suddenly all the metal cased appliances in your house are really dangerous. So what's the third solution? What's method 3? Method 3, we can have a live and a neutral supply, and inside the house we can have another wire going to each appliance, going to an earth rod. So now we've got our live wire, which is always dangerous to touch, our neutral wire, which is connected to the ground at the local substation. Then in your house, wherever you live, let's just say this is your supply here coming off. Inside your house you also have another wire that's going into the ground, okay, and then inside your house you've now got 3 wires. You've got the live wire, the neutral wire, and the earth wire in your house, but the earth wire just goes into the ground. Okay. Now if we follow the same argument as on the previous page, but instead of connecting the neutral wire to the case, we connect the earth wire to the case, then it still provides us with the protection we have before. If the live wire comes into contact with the metal case, current can flow through the earth wire, through the ground, back to the substation, hopefully blowing the fuse in the appliance, rendering it safe. However, if the neutral somewhere gets cut, the appliance doesn't become instantly live, because the appliance isn't connected to the live, the metal case isn't connected to the live or the neutral, it's just connected to the earth wire, and the earth wire is just connected into the ground. So this is safer than both the two situations I've described before. So that's why you would have a separate earth wire in your house in addition to the live and the neutral. Now, as I said, this is kind of a simplification from a physics perspective, a simple to give you an idea of what's going on. The reality is complicated and beyond even my knowledge and experience, because it's not my job to work in these situations, but I do know from my limited knowledge and experience that isolated electrical supplies are used for small scale applications but not for large scale electrical distribution. And actually a combination of so some countries use this method here, method 3, they actually use this exact method, but actually other countries use a sort of hybrid between method 2 and method 3, where actually the earth is provided by the neutral wire, but it branches off inside the house into a separate circuit to reduce the risk of the neutral becoming disconnected. So the reality of this is complicated, and there are lots of different systems in use in lots of different countries. However, the general principles I think that I've explained here should be right, which is that isolated supplies are inherently very safe but unpredictable if they're deployed over large scale applications where something could go wrong somewhere. Having a neutral wire being defined by shoving it into the ground somewhere then makes the live and the neutral very predictable in their behaviour, and then having an earth wire which is separate from the live and neutral means that your appliances are still safe if the neutral wire somewhere gets cut. It doesn't make your metal cased appliances all live. So it's quite a long explanation, that, and it's completely beyond the syllabus. There's no need to understand any of that for the GCSE or the A-level syllabus, but it might possibly answer some questions you had about why we've got these 3 wires and what is going on with these systems. So I hope it's helped a little bit. Post some comments if you want me to try and explain more, and I'll do my best.